What? It's upstairs. I had to hide it.
We'll figure it out.
Yep.
Grab the mic.
Okay, why don't we get started? So I'd like to welcome everyone to the 2022 edition of the uSTAR Summer Research Program. My name is Jim Skeet, and along with Jennifer Cole, we run the program. I'd like to thank all of those who are here today, both in person, but also virtually. I hope that people on Zoom can hear me because I'm usually the audio person checking audio, so I hope you can hear me. And I'd like to start the symposium with a quote. And it's a quote by Aristotle, and I think it's one of the best quotes I know about research. The students have all heard it before. And it's what we have to learn to do, we learn by doing. So if you don't know how to do research, as many, and for the students, for many of them, this was their first taste of real research. If you don't know how to do research, you need to do it before you learn how to do it. Which means what you're going to do is you're going to make mistakes, and the more mistakes you make, as long as you're thinking about what you're doing and why, the more you're going to learn, and the faster you're going to learn, and the faster you're going to become independent. The purpose of this program is really to give rising sophomores at WashU a taste of research, and as I said, for many of them, it's their first real taste of research, and really to see if they enjoy research, and this is something they might want to pursue further on in their career. I love running the program really for two reasons. One, for many of the students, it's a start of a journey, kind of a start of their kind of scientific academic journey. And two, the students are really amazing and they're incredibly fun to work with and engaging in terms of both intellectually and scientifically. So I'd really like to thank all of you, all of the students, for really diving headfirst into research over the summer, for your engagement, for your excitement, and for your curiosity about science, research, and the program. I certainly hope all of you made many mistakes. I hope all of you learned a lot. And most importantly, I hope all of you had fun in the program, in the lab, and probably most importantly with each other. Okay. I'd also like to thank the mentors, both in the room and on Zoom. And by mentors, I don't just mean the faculty members. I mean everyone in the host lab who helped train, mentor, and coach our students. The faculty, the postdocs, the technicians, the graduate students. I want to thank everyone for coaching, training, mentoring the students, and hopefully basically showing the students how to do research and hopefully how to have fun while doing research as well. The quality of our program is really defined by our mentors, and we know that we run a good program because we know we have a great set of mentors and labs into which our students can rotate. So again, thank you to all the faculty, the postdocs, the technicians, the graduate students for helping to train our students, for your expertise, your time, effort, patience, and support. We cannot run the program without you, so I just really want everyone to know that we greatly appreciate that. Okay, so for the 16 students in the front row, I'm going to repeat that at the beginning and end of every session, so just get used to it, because the mentors come and go throughout the day. With that, I'd like to start the symposium talk. So for 8 minutes, there's going to be, at 7 minutes, a 1-minute warning, which is going to sound like that. Okay. When you start, remember to screen share. Remember to talk into the mic because they can't hear you on Zoom without the mic. And I'm going to be up there monitoring audio, so if I can't hear you, I will tell you. Okay. Kira is going to introduce the first session speakers. Thank you.
Hello. So our first speaker today is going to be Kenzie Mounir, who is a part of the Catalano lab, and she will be giving her talk on the Mars 2020 science team, which is differentiating X-ray spectroscopy.
Is it picking up?
Hello?
Oh, do I have to hold it up?
Okay.
Oh,
Kenzie, leave it down and try it again.
hello?
Yeah, that works.
Okay.
Sometimes it'll depend how you're turning your head.
Okay. I'll try and like.
Yeah, but I'll tell you if it's not working.
Okay. Hello everyone. Thank you for coming this morning. My name is Kenzie Mounir, as Kira introduced me, and I had the privilege of working with the NASA JPL team on the Mars 2020 science team, and I've specifically worked on the Perseverance rover part of the Pixel team, and my main objective was differentiating X-ray spectroscopy. So to go into a little bit of the mission background, what we do, who we are, the Mars 2020 science team has mission objectives including finding signs of past habitability and prompting for sample return and finding geological history. Now, part of the Perseverance, or part of the Mars 2020 science team is the Perseverance rover, which landed around 2021. And on the Perseverance rover, there's the Planetary Instrument for X-ray Lithochemistry, or better known as PIXL, and I was part of the PIXL team. To give you a little background about the rover itself and the PIXL team, the rover landed in Jezero crater. Now, this is only a part of the crater. The crater goes all the way out here, and it was thought to be an ancient lake about 40 kilometers wide. Here is like the channel that goes into a delta area, and we thought the best place to find signs of past habitability would be around this delta region. So that's why we landed the rover there. And the main goal is to seek out signs of past ancient life, and we're using X-ray spectroscopy to find the abundance of elements in the target samples. So my main objective is tracking rubidium. Rubidium is a trace element, so it's not very abundant. It's very hard to track. And trace elements are actually very important because they can help us talk about the volcanism of the area and about the water that may have been present. Rubidium is also very chemically similar to potassium, which is here on Earth a lot, and it indicates the amount of fractionation, and it can tell us about decomposition and its geological history. But there tends to be a problem with the technique that we use. How X-ray spectroscopy works is the rover releases X-rays onto the target, and it detects the X-rays coming back. And they detect them in forms of alpha and beta energies. However, sometimes it detects two data points simultaneously, and it registers them as one data point. And this specifically happens with iron and rubidium. The iron K alpha and the iron K beta end up piling up, registering as one rubidium peak. So iron here is registered around 7 keV, and when it piles up, it looks a lot like rubidium, which is around 13.5 keV. And this makes it very hard to quantify the rubidium in our sample. So how do we fix it? We thought, let's see if we can find some kind of correlation between the iron K alpha peak area, the iron K beta peak area, our pile-up peak, which we'll call our imposter, and then our rubidium K alpha peak. We did this using MATLAB, which is a computer software that helps you code and write script. We graphed the data points and we fit it during using a Gaussian equation. The Gaussian curve creates a bell curve shape. So here are the individual data points in blue, and it fits with the red line. The first peak is the iron K alpha, and the second peak is the iron K beta. So at this point, we have our iron K alpha peak area and our iron K beta peak area. Now they should correlate because they come from the same element. So we did graph them, and we did find a strong correlation. So it tells us that our script is working and it's going well. So now we can move on and find better correlations between the other four things. We used the same script and we graphed the rubidium peak area. Now this is the one not differentiated with the pileup. And the data points aren't as accurate, or like the curve doesn't fit as accurately because there aren't as much data points as iron, because rubidium isn't as abundant as iron is. So at this point, we have our iron K alpha peak area, our iron K beta peak area, which we've established a strong correlation, and we have our iron pileup, and then our rubidium K alpha peak area. Let's see if we can differentiate between number 3 and number 4. So we thought, okay, let's see if there's some kind of connection between 1 and 3. And we graphed our imposter versus our iron K alpha, and we actually found a strong correlation between them using this specific equation. So just by knowing the alpha or the iron K alpha peak area, we can predict how much of that imposter will show up. But we had to make sure that this iron K alpha wouldn't be the same with the rubidium K alpha. So when we graphed it, we didn't actually find a strong correlation. So our equation would be able to differentiate between the iron K or the iron pileup and the rubidium K alpha. So finally, using that equation that we find between the correlation of the iron K alpha and the imposter, we hard-coded it into our script, telling it every time you make a rubidium detection, make sure you check it with our equation to find if it's an imposter or if it's actually the rubidium peak area. So we were able to finally get our our preliminary rubidium peak areas using that equation. So here we have our rubidium peak areas that are differentiated between our pileup peaks. And these are just different target samples going from Shop Hollow, Thornton Gap, we name them. And using this, we wanted to find the connection back to potassium, because potassium can tell us also a lot more about the geological history and everything else, because they're very connected. And when we use those peak areas, we found that with weight percent over 0.25 of the potassium, there's an actual high linear correlation. So the more rubidium, the more potassium. And using this, we can accurately assess the geological history on the Martian surface and find signs of past habitability. So this is just like a small puzzle, or a small piece of the puzzle, into finding more about the past of Mars. So I wanted to say thank you. Thank you for coming out here, especially to Jeff Catalano, Scott Van Wilmel, Abigail Knight, and of course the uSTAR program, Jim Skeet and Jennifer Cole. I want to also personally thank Abigail Knight. She helped me so much with this project. I didn't even know how to code before this. So thank you so much for walking me through it and being a big part of my first research experience. Oh, any questions?
What's the difference between the alpha and the beta?
Okay, so basically with X-ray spectroscopy, they shine the X-ray onto the atom and the electrons get excited, and so they reflect off of different shells. So depending on the shell it comes from, it shows if it's like, it releases the alpha energy or the beta energy. Any other questions?
Hi Kenzie, that was nicely done. Do you know, with your rubidium peak, so after you did the equation that separated it, gave you those nice peaks, do you know how much of that surface area of Mars is covered from that data? Is it a small area where you're getting the bounce back and getting those peaks from, or?
So the X-ray spectroscopy uses a point-by-point basis. So this doesn't show like the whole surface area of Mars now. We just landed in like a specific part of the Jezero crater. So I don't have the exact dimensions, but it's like a point by like everything is grouped. Like Thornton Gap 1, Thornton Gap 2 is one location. And then you have like the debris like in another area. So these are like ranging areas of the delta area.
But you don't know, like each peak, you don't know like the size of that area, these different names that you're getting the reading from? I was just
No,
curious.
I don't have the exact
Okay,
dimensions.
thanks.
They're like the size of postage stamp.
Oh, okay, thanks.